for the first order reaction, we're going to have inertial logarithm of what? Of concentration of what? Of A of t, which is the A final, right? This is going to be equals to what? Minus kt, k1t, because it's first order reaction, and this k1 is actually what? The raised constant for first order reaction. Then we're going to have this to be plus inertial logarithm of what? Of concentration of what? Of A naught. That's the first expression I want you guys to understand, to how to know. Then if you don't like this formula, another formula that you can use is actually what? Is actually log to base 10 of concentration of what? Of A of t, right? This is going to be equal, you're going to have minus k divided by what? 2.303, right? You're going to have 2.003, then plus what? Log to what? To base 10, right? Of, let me simply say, concentration of what? Of A naught. That's what you're going to have. So if you don't like this, you can go ahead and use what? The second one. But the one I prefer most is actually what? The first one, because I don't need to stress myself at all. Right? Because it's quite similar to what? To zero order reaction. I'm just putting inertial logarithm to what? To the concentration here. Now the third expression is actually for the half-life. Half-life, which is the T half, is actually what? 0.693 divided by what? Divided by K. That's for the half-life. You have to bear that in your mind as well. And in some cases, they might ask you to calculate for what? For the slope. So without stressing yourself, you can actually have slope K to be equal 1 over T, right? Inertial logarithm of what? Of this is going to give us what? We're going to have inertial logarithm of what? Of concentration of what? Of A naught actually divided by what? Concentration of what? Of A final, or A of T. That's what you are going to have it to be. So you can just take note of what? Of these four expression. It's very important, and you need to know that the rates, the SI units for the rate constant for first order reaction is actually what? Per seconds. That's another important fact that you need to know. So now let's just go ahead and solve the question, right? Let's go ahead and solve the question that we have. Now let's take a look at the first question I'm having here. The question says, for a first order reaction, if the rate or rate constant K is 0.693 per second, what is the half-life of the reaction? And we are given the option here. Now, first thing you're going to do is that we are asked to calculate for the half-life, and we know that the expression for half-life is actually T half, which is equal 0.693 divided by what? K. And the reason why I'm using this is because from the question, it is mentioned that the reaction is first order, and the expression for half-life of first order reaction is actually given as T half equals to 0.693 divided by what? K. And K is actually what? The rate constant. Now from the question, I'm giving that the rate constant K is 0.693, right? So if I'm going to put it here, I'm going to have T half to be equal, which is the half-life, equals to 0.693, right? Then divided by what? We are going to have this to what? K. K is actually 0.693, and everything here is actually what? Per seconds, right? So from there, I'm going to have this to be actually, this is going to give us T half is going to be equal, you know, this is going to cancel this. Then we're going to have T half to be equals to what? 1 divided by what? Per seconds, right? So if I bring this one to the front, I'm going to have this to be what? T half is going to be equals to what? 1 seconds, and that's going to be what? Answer. So the answer, the right option here is actually what? Option A, right? Now let's go ahead and take a look at the next question that we have. The next question I'm having here says, for a reaction with a rate constant of 2.31 multiplied by 10 raised to the power minus 2 per minute, what will be the concentration of reactant A after 14 minutes if the initial concentration is 1 molar? Now what we're going to do here is that we are actually giving the what? The let me simply say the time. We have the time here. Then we also have the what? The rate constant here, right? Then the next thing is that we are giving the what? The initial concentration to be 1 molar. So if you recall the expression for first order reaction, and that's given by what? Inertial logarithm of what? Of concentration of what? Of A final, right? A of T rather. You can put A of T or A final. This is going to be equal minus K1T, which is the rate constant multiplied by what? The time, then plus inertial logarithm of what? Of concentration of what? Of A initial that you're seeing here. Right, so if you go ahead and put in the parameters that were given from the question into this expression, we're going to have inertial logarithm of A final is actually what we are asked to calculate for, right? Because the question says what will be the concentration of the reactant after, that is the final concentration of the reactant after 14 minutes, and that's what we are asked to calculate for. So we're going to have inertial logarithm of A of T. This is going to be equal minus K here is actually going to be 2.31 multiply by 10 raised power what minus 2 per minute. Now the question is, we are going to have this to multiply by what time. The time is actually what 40 minutes. Now some people will be like, should I convert this into seconds? If you convert this into seconds, that shows that you have to convert the rate constant also into seconds, and that's going to take a long time. So you just have to use it directly. So you're going to have minus 2.31 multiplied by 10 raised to the power minus 2. This is going to be multiplied by what 40, right? Then we are going to have plus inertial logarithm of A naught is actually what 1 molar, as you can see here. So I'm going to have what 1 here, right? Now let's go ahead and simplify this expression. We're going to have inertial logarithm of A of t is going to be equal. So multiplying everything here, we're going to have negative 2.31 multiplied by what 10 raised power what minus 2. And then we're going to have this to be what to be multiplied by 40 again. Then we're going to have plus inertial logarithm of 1. Let's see what we're going to have here. So everything we're going to have here should give us approximately minus, this is going to give us minus 0.924. That's what we are going to have. Now in order for us to get the constitution of the reactant, we have to take what exponential of both sides. So taking exponential of both sides, let's see what we're going to have. The natural logarithm is going to cancel this exponential. Then we are going to have the final answer to be equals to what is going to be constitution of A of t, which is the A final, right, is going to be equals to what exponential minus 0.924, right? Exponential minus 0.924. Let's see what it's going to give us. It's going to give us 0.924. We're going to have that to be 0.396. So the constitution of the final constitution of the reactants is going to give us it is actually 0.396, right? That's actually the answer, 0.3969, right? So that's actually the answer. Now if you look at this very well, I think option A to be the answer, right? It's actually as a result of maybe my mistake actually, right? So from here, this option should actually be 0.3969. And if that's actually the case, that shows that option A is what is actually the answer, right? So now let's move to another question. Now let's take a look at the next question I'm having here. The question says, what's the SI units of the rate constant for a first order reaction? Now it's very simple actually. What we just have to do here is just to go ahead and maybe write the rate expression for first order reaction. And if you're going to write it, rate is actually equal, right? We're going to have K, then multiply was constitution of A. A is the reactant, right? Then that shows that we should have this to be raised power of 1 since it is a first order reaction. So this actually was the rate expression. Now from there we have to make the rate constant K the surrogate of the formula. That's what we just have to do here. So from there I'm going to make it the surrogate of the formula. I'm going to have what K to be equal. We're going to have this what rate, right, divided by what constitution of the reactant, which is this they are saying here, raised power of 1. Now the next thing I'm going to do is actually to write find the rate expression for this reaction. The rate expression in terms of let me simply say first order reaction. We should know that whenever we are given a reaction that will occur between A to give rise to B, as you are seeing here, that shows that what we are going to have is actually what rate is going to be equal change in what constitution of A with respect to what changing what in time. That's exactly what we're going to have, and that's what it means. That is, there is going to be what changing constitution of this A with respect to what to time, and the change is going to be what a negative change, because A we have to reduce with time and B we have to increase with time. That's exactly what you have here. So from there, what I'm going to be doing is that this constitution that you are seeing here simply represents what let me just say simply say the SI unit for the constitution of the reactant here is actually what in molar. Then we are going to have time, that's seconds. That shows that for rate we have to molar per seconds here. That shows that that's what I'm going to have. I'm going to have K, right? I'm going to have K, which is going to be here. K is going to be equal. We're going to have molar over seconds, then multiply by what? Now we are going to have 1 over here is also molar, because for any concentration is either you have it in form of molar, or you have in form of mole per dmq, right? Or you have it in form of mole per liter, right? You can have it in that. That's just for concentration. Now if you look at this very well, what's going to happen here is actually this molar here is going to cancel the molar here. Then the final answer that we're going to have is going to be K is equals to 1 over seconds, which is also the same thing as as per seconds, and that's what? That's B. Right now, the simplest method you can use if you don't want to stress yourself, it's actually work for all integrated expression, rate expression, whether it is first order, it is zero order, or it is what? It is second order. You can actually use what? You can use molar raised power what of 1 minus n, right? Then multiply what? Per seconds, right? Where n is actually what? N is actually the let me simply say the order of what? Of the reaction. That's n. So if it is first order reaction, that's so that n is going to be equal to what? 1. If it is second order reaction, that's so that n is going to be equal to 2. If it is third order, n is going to be equal to what? 3. And if it is zero order reaction, n is going to be equal to what? 0. Now for this question, n is actually what? First order reaction, and n is actually what? 1. So if I put it here, I'm going to have what? M raised power what? 1 minus 1. Then we're going to have second 1 minus 1. Actually, I need to put 1 here, right? So we're going to have 1 minus 1. And that's going to be what? This we are saying here, then per seconds. That's what we are going to have. X is power minus 1. Now, 1 minus 1 is actually what? 0. That's what I'm going to have this what? M raised power what? Of 0. X is power what? Minus 1. And n raised power 0 is actually what? 1. And that shows that we are going to have just ordinary what? Per seconds, which is actually what? This that you are saying here. So you can go ahead and use what? And use M raised power what? Minus 1 minus 1 minus n. Then X is power what? Minus 1. It works very well. Right? So that's just it. So now let's move to the next one that we have. Now let's see another question that we have. The question says, a reaction is found to be first order reaction with respect to reactant A if the concentration of A decreases from 0.8 molar to 0.2 molar, as you can see here, in 30 minutes. What is the rate constant? And we asked to calculate for the rate constant here. Now the thing is that we are going to record the expression for first order reaction. Initial argument of concentration of A of t is going to be equal minus K1t, right? Then plus initial argument of concentration of A of O. So if we use this expression, it's going to take us a lot of time actually, right? It's going to require a lot of time for us to actually solve it because we have to simplify here. So in that case, I will just go ahead and use this one directly because I think it's going to make sense to us if you actually use this expression I'm going to write. So since we are asked to calculate for the rate constant as from the question, you can simply use rate constant K1, which is rate constant for a first order reaction is equals to what? 1 over t, right, which is the time. Then we are going to add this to multiply by what? Initial of concentration of what? Of A naught, right, divided by what? Concentration of what? Of A of t, which is the A final. This is basically the formula that I'm going to use instead of what? Of this, because this will actually take me a lot of time, right? So I'm not going to use this. So that's so that all these formula, you have to understand them very well and how to apply them as well, right? So it's very, very interesting. You can go ahead and use the first one as well, but it does that it's going to take a lot of time, and this is objective question. That shows that you have limited time to solve it. So let's just go ahead. So from there, we have to calculate for the constant. I'm going to have K1 is going to be equals to 1 over time. The time here is actually what? 30 minutes. Do I need to convert? No. You are going to have 1 over what? Over 30. This is going to be what? Multiplied by initial what? Of this is going to be what? This is for the initial concentration, which is actually 0.8 because it decreases from 0.8 to what? To 0.2. So initial concentration is going to be what? 0.8, right? We're going to have 0.8 here, right? Divided by we have 0.2. So I'm going to put it here 0.2. That's what you have to know. Now from there, we just need to go ahead and solve this, right? So solving this, let's just see what we're going to have. We're going to have the rate constant to be equal 1 divided by 30. That's what's going to be. This gives us about 0. We're going to have to work with 0.033, right? That's our key. Then that's our this expression here. We simplify it, right? So we're going to have this to multiply by what? Let me just simply press initial argument of what? Of this is going to be 0.8, right? Then divided by what? 0.2. Let's see what we're going to have. So we're going to have this to be multiplied by 1.3862, right? That's what we're going to have. Then we can now multiply this together. We're going to have this to be what? To be multiplied by 0.033, right? So and we are going to have the answer. The final answer is going to be equal to 0.045457. That's going to be the final answer. Now, one thing I want you guys to understand here is that if you go ahead and look at this very well, since we are dealing with what? With the rate constant K1, and that shows that we are going to have the SI unit to be in form of what? Of seconds per inverse. But since we are actually giving it in what, in minutes, so it's going to be what, it's going to be minutes per inverse. Inverse, that's what we're going to have. That is going to be import in per minute. Now, what's going to be the right option here? This is not the right option, right? This is 0.00462. This should be the right option. But for now, let's just look at another one. This is not the right option, and this is not the right option. So if we approximate this, we're going to have it to be 0.046, right? So we can actually go for option B, which is the right answer. Now let's move to another question that we have. Now let's see another question that we have. The question says, a first order reaction has a rate constant of 0.045 per minute. Then from there, how long will it take for the concentration of the reactant to reduce to 25% of its original value, or simply you say its initial value, right? Now what we just have to do here is just to go ahead and do some manipulation here. Actually, it's not manipulation, just go ahead and solve it. Now from there, let's just bring out the parameters. We are given the rate constant K to be equal 0.045. That's the rate constant. How long will it take? We are asked to calculate for the time, because the question says how long the time it will take for the concentration of the reactant to reduce to 25% of its initial value. Now what this means is that if initial value of the reactant is actually A, right? The initial value is A, then how long will it take A to reduce? That shows that if you have the initial concentration to be A naught here, right? That shows that we are going to have the final concentration to be 25%, and that's going to be 25 divided by 100, then multiply by concentration of A naught. That's exactly what we're going to have this one to be. That's 25% of the let me say of the original value, and that's what you have here, right? So that shows that I can just simplify it to be concentration of A final, right, to be equal. We are going to have it to about 0.25 that of A naught. That's what we are going to have. Right, now let's go ahead and bring out an expression for an expression that we can actually use here, right? So if I'm going to use the original expression, it's actually going to take me a long time, right? So I'm going to basically use the first one. I can actually use KT, right? KT, right? Then I'm going to have it to be, let me simply say this is going to give us inertial logarithm of let me say this concentration of A divided by concentration of A final, right? Concentration of A final. That's what we are going to have, right? Now we are going to have this to be KT, and then by the variable side, I'm going to multiply both sides by 1 over T. Then let me just simply say I multiply both sides by 1 over T, right? So I'm going to divide it by sorry, it should be 1 over K, because I'm asked to calculate for the time, right? So I'm going to have 1 over K here, I'm going to have K here. This is going to cancel this. Then from there, we've successfully eliminated K here. That's that we make T the result of formula directly. So we just have to put all the parameters to this formula that you're seeing here. So we are going to have T to be equal inertial logarithm of concentration of A is actually the initial value that we are talking about, and it's still is still intact, right? It's still the original value. Then divided by the final. The final is going to be 0.25. Then multiply initial concentration. That's what we have. Then this is going to be multiplied 1 over K. The K here is actually 0.045. So what we just have to do here is just to simplify, right? So that shows that in the course of simplifying here, we're going to have this one cancelling this one here, right? Because they're actually of the same. So now the next thing I'm going to do is just to go ahead and simplify everything. So if I'm going to simplify everything, this is what I'm going to have. I'm going to have this to be inertial logarithm of 1. That's what we're going to have at the first side. Then divided by 0.25 multiply 0.045. So now let's just go ahead and multiply all this and see what we're going to have. So we're going to have a natural logarithm of 1, right? Then divided by we're going to have this to be 0.25, then multiply by 0.045. So here we're going to have the answer to be actually, so natural logarithm of 1 should give us, that's going to give us, we have it to be 0, right? That's good. So we're going to have this to be 0, right? Then this is going to be divided by anything divided by 0. So the answer is still is still 0, right? So the answer to this question is actually is actually 0, right? Because whether whether we try to find it in one way or the other, or simply just go ahead and do it like this, So let me just go ahead and just say natural log of 1. Let's see what we're going to have if we actually try to simplify it like this, right? Let's say we simplify it to be a natural log of 1 divided by what? 0.25. Let's do it one by one like that. So if we are going to have a natural log of 1 divided by what? 0.25, let's see what's going to give us. The answer is actually something. That's why we should be able to get something here. So we're going to have this to be equal. From here, now, we're going to have the answer to be equal. This is going to give us 1.386. Then, from there, we're going to have multiply by what? 1 over 0.045. So, let's just see if we are going to have it. So, that shows that if you solve it directly using a natural log of 1, that's a math error, right? You're not going to get the answer. So, this is an error. Everything here is an error. So, you just have to cut it out, right? So it is an error, right? So now let's just go ahead and solve this. So we're going to have this what? 1 over, let me simply say 1.386, right? Then divided by 0.045. Let's see what's going to have. So here we are going to have the answer to be 30.8, right? So if we solve it, this is going to give us 30.8. Then we're going to have per minute, right? So that's what we're going to have. So that shows that in natural log of 1 over 0.25, we have to take it separately before we actually go ahead and say we are multiplying anything here, right? So it's very, very important actually, because we need to apply logarithm identity. I failed to apply logarithm identity here. I just solved it directly because this is actually what ln A B, which actually was ln A plus ln B. I just solved it directly, and which is why I did not get the answer. So the answer to this question is actually what is not option A, is not option C, and it's not option D. It's actually what option B. And that's just it. Now let's solve another question. This is going to be the last question I'm going to solve in this video. And if you want more challenging questions, or you want to watch video on how to solve a challenging question when it comes to first order reaction, I'm going to drop the link to our Patreon account in the comment section below, so you can actually visit our Patreon account. We have a lot of questions on first order reaction, second order, third order, and also zero order reaction. So you can actually watch the videos out. You're going to find this more interesting. And one thing about our Patreon account is actually that the video available on our Patreon account is actually totally free. So you can just visit our Patreon account. You're going to see a lot of questions, a lot of videos we made under chemical kinetics, and also some mathematics as well. So that's just it. So now let's go ahead and see how we're going to solve this question. And if you want to try this question out, you can actually pause this video and do it to try it out. But make sure you drop the answer in the comment section below. Now the question says a first order reaction has a rate constant K. We are given rate constant K here, right? Then if the initial concentration of the reactant is, now the initial is going to be what? Concentration of A naught is going to be, that's going to give us 0.6 molar, right? How long will it take the concentration to drop to what? Now how long will it take the concentration to drop to? Now we're now having final concentration to be what? 0.075. Then the question says how long, which is t. We have to calculate for t, given that the k is actually what? 3.5 exponential minus 3, right? So that's what we have to be our k. Then what we're going to do is just to record the expression. Since we're asked to calculate for time, we can simply use kt equals what? Inertial log of 0 of simply, let me just go ahead and record the formula first, right? So we're going to have inertial log of concentration of A naught, right, divided by what? Divided by A final. That's what we have, right? We're going to have this to be, we can just multiply both sides by what? By k, by 1 over k, right? So I'm going to have multiply what? 1 over k. So that shows that in this scenario, this and this is going to cancel out. Then we're going to be left with t, right? So let me simply rub it like that. So now let's go ahead and solve it. Now we're going to have this t, which is the time that we're asked to calculate for, to be equal. Inertial log of initial concentration is actually what? 0.6 divided by the final concentration is actually what? 0.075. That's what we have. Then multiply by what? 1 over, we're going to have k to be 3.5. Then times 10 to the power minus what? Minus 3. That's what we have. So we can just go ahead and simplify this. So we are going to have this to be, let me simply press this one together. We're going to have inertial log of, that's going to give us 0.6 divided by what? By 0.075. So we should have this one to be, that's 2.079. That's what we have. So we're going to have this to be 2.079. Then we're going to have multiply by what? 1 divided by what? 3.5 exponential minus 3, right? So let's go ahead and simplify this. We're going to have 2.079, then multiply by what? This is going to be what? 1 divided by what? 3.5, right? Exponential minus 3. Let's see what we're going to have. So the answer we have here is actually what? 594, right? That's actually the answer that we have. So everything here is actually the same thing as writing what? Is actually 594. That's what we have. Now if you look at this question very well, the answer, the options are wrong actually, right? The options are wrong, but before you actually conclude whether the options are wrong or not, we can actually go ahead and check again, right? It's very important for us to check the expression very well. The formula we use, yeah, we are right. 0.6 divided by 0.07. Let me just do it first. Let me just do it one by one. 0.6 divided by what? 0.075 to see what we are going to have. That's 8. Then inertial logarithm of 8. Let's see what we're going to have. We have it to be 2.0794. 2.0794. Let me just add 4 here, right? Then let's just go ahead and multiply everything. 2.0794, right? Then this is going to be multiplied by, let's say we have this. Let me just simply go ahead and do it directly. We're going to have 2.0794, right? Then divided by what? This is going to give us, divided by, let me simply say, we are going to have this to be 3.5 multiplied by 10 raised power what? 10 raised power. This is going to be 10 raised power what? That is going to be minus 3. So the answer that we have here is actually 594, and that shows that the options here are wrong, right? And the answer is what? Is 594, right? Then we're going to have it to be 594 seconds since we are asked to calculate for time. So that's just about this video. So if you find this interesting, I have a lot of video on that chemical kinetics. You can go ahead and visit the playlist. We have many videos that we already made here. So that's just it about this video. If you like it, make sure you subscribe, and don't forget to like, share with your friend. Some of your friends will find chemical kinetics a very difficult topic, so you can actually share it to your group and some other social media platform. So that's just it. Thanks for watching.